Hello and welcome to this video in which we analyze the forces that a hammer applies to a nail as you're trying to pull the nail with the hammer. And you can see we have a picture of a hammer pulling a nail. We'll analyze this to see what forces are applied, and then we'll also analyze the case if you've done much carpentry or reading. In order to pull a particularly recalcitrant nail, it turns out that you're advised to put a block, something like this, between the hammer and the wood to pull the nail. And we'll see if that really does help you pull the nail. So this is going to be pretty much a straightforward analysis in which we will look at static equilibrium. We will neglect the weight of the hammer because relative to the other forces involved, the couple pounds of the hammer is just not going to be significant. So I guess let's begin. Let's suppose that we have a 30-pound force applied on the handle. So somebody's grabbed the handle and they're pulling it towards the right. And the idea is that they're trying to pull up this nail in this block of wood. So the first thing we need to do this analysis is identify. We'll use the hammer alone as a free body diagram. In fact, I'll draw here some cuts to show that we're not going to include the block or the nail. And the forces then that we need to look at, we'll assume that at this point where the hammer is resting on the block, that we have just a vertical force. And in fact, to name these guys, why don't we call this point A, we'll call this point B, and up here on the handle we'll call this point C. Okay, so our force at point A will just be Fay. Again, the assumption here, which isn't that great an assumption but is reasonably accurate, is that the block of wood represents a frictionless surface to the hammer. And again, that turns out to be an okay assumption. It's probably not the best, but if we don't make that assumption, then the problem's not statically determinate. Okay, at B, we'll assume that the nail applies a force to the hammer that has both an X and a Y component. And we need to solve for what those are. In order to solve the problem, we'll put, let's see, what's a good color for axes? We'll set point A to be the origin of a coordinate system. So we'll have an x-axis like this, and a y-axis. Oh man, looks like a drunken y-axis. Here, we'll force this y-axis to be nice and straight. Okay, so we have a y-axis like this, again with point A at the origin. Okay, so in order to solve this, we need to we'll use vectors to solve it. So we need to get position vectors for the 3 points where the forces are applied, for point A, B, and C. The position vector for A is just 0, 0 because it's the same as the origin. So for C, our position vector, we have here an angle of 15.6 degrees, and so and we have a distance along the handle of 10 inches. So our position vector, the x component, is going to be minus 10 inches sine of 15.6 degrees. This will be I hat plus 10 inches cosine 15.6 degrees j hat. And when you work this out, you get minus 2.69 inches I hat plus 9.63 inches j hat. Okay, so that's the position vector for point C. We also need a position vector for point B. So we'll have RB, and again this is the position relative to the origin, which is point A. So RB, the angle between this line here and this line here is 42.2 degrees. So the angle between the vertical and this line is, 57.8 degrees. So we'll have RB is minus 2 inches. That's the length between point A and where the nail is contacting the hammer. Sine, and this again is 57.8. That's the sum of those two angles. I hat plus 2 inches cosine 57.8 j hat. And when I work this guy out, I have then minus 1.90 inches I hat plus 0.628 inches j hat. Okay. And now we can get the, we are going to compute moments, or a moment, about point B. And the reason I want to compute the moment about point B is two of my unknown forces, Fbx and Fby, go through point B. The only unknown that doesn't go through point B is Fay. So if I compute the moment about point B, then that will actually give me one equation. I'll set it equal to 0 because we're under static equilibrium conditions. I'll set that equation equal to 0, and that will allow me to find out then what Fay is. So to compute the moment about point B, I need the relative vector from B to A. So I'll denote this relative vector. Actually, let's do B to C first. So the relative vector from B to C is going to be RC minus RB, which when I subtract these two, I get minus 0.79 inches I hat plus 9 inches j hat. Okay, so again, this is the vector. If I draw this, it's basically this guy right here. And this is RBC. And the nice thing about this is that I'll now be able to take the cross product of RBC and this vector representing the 30-pound force on the handle to get the moment about B generated by this force. So similarly, I will need RBA, that is the vector from B to A. And since A is the origin, this is just going to be minus RB, which is 1.90 inches I hat minus 0.628 inches j hat. Okay, so we're close. The next thing I need is I need the force at the handle, this guy right here. We're assuming that this force is applied at a right angle to this line that goes through the axis of the handle. And so let's call this force, say, FH, for the force applied to the handle. And if I look at my geometry here, because this is a right angle, then I have that FH forms an angle of 15.6 degrees with the horizontal axis. So with that, I can say then that FH is 30 pounds cosine 15.6 degrees I hat plus 30 pounds sine 15.6 degrees J hat. And we work this out and we get this is 28.9 pounds I hat plus 807 pounds J hat. And finally, the force at A is just going to be the magnitude of its y component times J hat. So now we have everything we need in order to compute moments about B. So I guess we'll just do that. And again, the idea is we want the sum of the moments about B. We know since we have static equilibrium, we'll want to set this equal to 0. Okay, so the sum of the moments about B, we have RBC. This is the position vector from B to C, cross FH plus RBA cross FA, and again we're going to set this equal to 0. Okay. So without actually working this out, since I'm kind of running out of time, you can go to Wolfram Alpha or your favorite method of computing cross products. We get that this term, when we do the computation, is minus 266.5 inch-pounds times K hat. And this guy here is plus FA, the magnitude of the force at A in the y direction, times 1.9 inches, again times K hat, and we have to set this equal to 0. And from this then we can solve for FA y, and we get that FAY is 266.5 inch-pounds divided by 1.9 inches, so it ends up being 140.3 pounds. Okay, so we've gotten FAY. We still need to get FBY and FBX, but I'm out of time, so this will have to happen in part 2 of the video. See you there.